Welcome students, my name is Reinhold Leinfelder from the Institute of Geosciences of the Free University in Berlin and from the Rachel Carson Center for Environment and Society of the Munich University. Today we're going to deal with lecture 2 on global megatrends, and we mainly focus here on the first chapter of the WBGU report on World in Transition, a social contract for sustainability. So we have 3 episodes. The first one, this one here, will be on megatrends of the Earth system. The second one to follow is on megatrends of the global economy and society. And then we're going to have an interview where we're trying to tackle some of the open questions. So I hope what you will learn here are a couple of things. First, why the term Anthropocene might be the appropriate name for the present and the future when dealing with global megatrends and their transition towards sustainability. Second, which factors and processes drive the Earth system towards endangerment of our society? And then why planetary guardrails such as the 2-degree centigrade goal might be a useful tool to help keeping the planetary system with its natural boundaries. And at last, I hope we will learn about the interaction and interdependencies and feedback loops of humankind-driven natural processes. So the contents will be, in brief, the Anthropocene concept, the planetary boundary and guardrail concept, climate change trend and related issues, trends on land degradation and desertification, water shortage, water pollution trends, raw materials, nutrients, pollutant trends, and then on interaction and feedback loops. So let's start with the Anthropocene concept. This is a name for a suggestion for a new geological age, the age of humankind. And you might be familiar with this image from the NASA, where the activity of men across the Earth is here highlighted by all these lights across the Earth. But let's come with a couple of figures just to explain this concept. For instance, only 23% of ice-free land is still pristine. That means we used up the land, we use it now, or we have used it, so it might be degraded. So wildlands really are not much left. A couple of more figures here. The first one we know already. 77% of the land surface is used by humans or has been used by humans. Up to 50% of available fresh water is used or controlled by humans. We do have a severe overfishing worldwide. We won't tackle this problem here owing to time constraints, but just to mention it, we have 100 to 1,000 times higher extinction rates of animals and plants than would be the natural rate here. And this is an impressive figure. Biomass of humans and its domestic animals amounts to 90% of biomass of all living mammals. Increase of energy consumption since 1900 is 16-fold. You might know that since 400,000 years or even longer, we have the highest atmospheric carbon dioxide concentration and methane concentrations in the atmosphere. Nitrogen oxides and sulfur dioxide emissions are now higher than natural sources. And now this is for geologists. The mean erosion rate since 500 million years, this is what the geologists can calculate, was something like 24 meters per million year. And today, if we would just calculate it for the next million years based on the present erosion rate which we cause, it would be up to 700 meters per million year. So we can really say humankind has become a major geological, a major Earth system factor. The idea of the Anthropocene concept is from Nobel laureate Paul Cruzen, and he said already in 2000, man has become a geological and Earth system factor, so he is not against nature, he's part of nature. That means that the Anthropocene concept, the Anthropocene age can be geologically defined, and we really preserve fossils of the Anthropocene. But it also means that science has to tackle the Anthropocene in a completely different way. We have to have a really systemic view. We have to combine natural, social, economic, cultural sciences with humanities, technology, with art, with experienced knowledge, with indigenous knowledge, all into one concept. But from this, we also have to assume our responsibility for the future. And this is not just an empty sentence. This means we have to design the present at the very moment for a sustainable future on a knowledge basis. We all know that we don't know enough yet to understand the world. So that means we have to continuously readjust the world. As a whole, we have to learn from all sources which we can, and since we're speaking about a new age, a new time, we have to learn from time scales. That means we have to learn from the past, history of the Earth, human evolution, cultural evolution, technical evolution, as well as from the present situation and trends and future scenarios and models, which we have already established. So in brief, the key responsibilities for the Anthropocene are that we don't have this dualism, the good nature versus the humankind, mostly the bad humankind with the bad culture anymore. So we are one system. It also means that there's no way back to the Holocene, to that time, that relatively environmentally stable time after the last ice ages. No, we entered a new age. And of course, no simplistic solutions are available. Systemic thinking is needed. So the Anthropocene concept, I believe, is a real good metaphor for our flagship report, where we need a transition towards sustainability. This is why the WBGU also uses this Anthropocene concept in its report. So let's go to the trends, but first have an overlook across the planetary boundaries as defined by Rockström in 2009, and this follows up the guardrail concept, a much earlier concept of the WBGU, and it should tell you that we have a lot of different problems in our Earth system, quite some of which we have mentioned already. So climate change, ocean acidification, and so forth. I'm not going into details here, but you see the red areas here, and this means after quantifying the problems, we can come up, or we should come up with some boundary ideas, saying if we cross these boundaries, this will be crucial, this will be very difficult for the Earth system. And I would like to show you a couple of trends here. You see red colors, you see some green colors. That means not everything is so bad yet. And you see some areas where we don't have any idea yet because we couldn't quantify, for example, chemical pollution or pollution in the air. So let's follow this concept through some trends which we are going now to present. Now this one is on climate change and related issues. Climate change is so important that we will have a whole lecture, lecture 3, on this topic. So I will just tackle some issues related with climate change. For instance, this one here, this shows you the projected rate of range shifts in marine organisms, either more living on the floor or in the water column, caused by climate change up to 2050. And this really are dramatic figures. We will have shifts of more than 4, maybe even more than 6 kilometers northwards per year, which will cause huge problems with fisheries, but also with biodiversity as a whole. Another issue related to climate change is the acidification of oceans. Many organisms need proper pH values. This is the plankton, these are the coral reefs, and many other organisms which secrete calcareous skeleton. And you see up on that uppermost map the situation of coral reefs, these blue dots, in 1870. You see a lot of dark green colors, and this means this was a really appropriate situation for the corals in terms of pH values. 2005, which is the middle map here, you see the situation has already changed. Still green colors, but light green colors, still appropriate but not perfect for coral reef growth. And if we have the projection on the lowermost map for 2065, you see that acidification has removed here all the green colors. That means that the coral reefs won't be able to thrive here, won't be able to grow. And this is but one of the problems coral reefs have at the very moment. So acidification adds to other problems in this field. This leads us to the next trend, ecosystem services and biodiversity loss. You certainly will know about ecosystems goods, just a few examples: food, fibers, building materials, industrial raw materials. And if we remain with the coral reefs, just think of the pharmaceutical materials which we can find in coral reefs, like antibiotics and much, much more. Examples of ecosystem services are protection. Again, for instance, the coral reefs which protect against high waves, as do the mangroves, for instance, or freshwater supply, soil fertility, unpolluted air, or pollination, just to mention a few examples. We have started to identify the values of ecosystem services. This is a difficult approach, but it can be done, and it has been done recently. So I'm not going into all these details here, but this table should tell you, should show you that there's a high value of the various ecosystems. For instance, coral reefs have the highest value, of course, but grasslands still have a value which in comparison to coral reefs is lower. But the interesting thing is here that once they are damaged or they are at least deteriorated, so you might be able still to restore them, this gives you a lot of costs. So for coral reefs, the costs are very, very high. A damaged coral reef to repair is a huge enterprise here. So the benefit cost ratio, which you see on the left column in coral reefs, is still positive, but it's something like 3:1, whereas in grasslands, which are cheap to restore, the benefit cost ratio down there on the table is 75:1. So it's really worth maintaining these ecosystem services also on an economical view. If we lose ecosystem services, that means we lose biodiversity, because both is very closely related. So drivers of biodiversity loss is land use and freshwater management, overexploitation of oceans, pollutions of all kind, climate change, acidification of oceans, invasion of alien species by human infrastructures, and of course especially the speed of all these changes. Just to come up with some figures, endangered to extinct are 22% of mammals, 14% of birds, 31% of amphibians, 28% of conifers, or even higher values for other plants, and we really could continue this list for the next half an hour, if not longer. In this map here, you see areas which we use for agriculture. This is in orange or in green, and depending on the darkness of these colors, either more than 50 or either more than 85% is used by humankind just to produce goods for us, for agriculture, for cattle and so forth. That means we really are sitting on major parts of the world where we have changed the ecosystem, and these are interestingly the areas with the highest biodiversity loss. This figure shows you this. Now, I'm also not going into details here. What is shown here is that we today have, rather than biomes, anthromes. So we have changed our biological systems here. And if you just go to the biodiversity row, which is down there, you see that biodiversity is actually today higher in most cities, in most urbanizations, than it is in the agricultural fields. That really is just an image to highlight how important it is to have another kind of agriculture to maintain biodiversity values. So how about guardrails and institutions involved in biodiversity preservation and ecosystem preservation? So Rockström and al. Suggest a planetary boundary with an extinction rate which should be a maximum of 10-fold of the natural background rate. As we have heard already, the current status is 100 to 1,000 times higher. The WBGU guardrail is a different one. It says that we should protect 10 to 20% of area on land and 20 to 30% on the sea. There is the UN Convention on Biological Diversity, and in its Nagoya Protocol, the targets are on land 70% and marine areas 10%, which to our view is definitely too low, especially in the marine areas. Let's move on to land degradation and desertification. The main drivers here are deforestation, overgrazing, expansion of non-suitable agriculture, soil salinization, soil sealing, and of course urban growth. So the annual loss of productive land is up to 50,000 square kilometers, and desertification has already released carbon from the soils up to 103 gigatons of carbon dioxide. Sustainable management and restoration of grassland would really help. We've learned about this already. Storage capacity, annual storage capacity would be up to 800 megatons of carbon dioxide per year. Again, do we have guardrails or institutions involved to protect this? Well, yes. Rockström planetary boundary is about 15% of the total global terrestrial area should be used for agriculture proper, and the current usage for this closely defined agricultural area is now nearly 12%, so there's not much left here. The WBGU guardrail comes up with a different suggestion. It says that soil loss should not exceed soil reformation. That means, for instance, for the temperate zone, that a maximum of 1 to 10 tons of soil loss per hectare per year should not be exceeded. We do have a UN convention. This is the UN Convention to Combat Desertification. It is considered to be the weakest of all Rio conventions. It only addresses drylands. Wetlands, forests are to some extent covered by the Convention on Biological Diversity, but we have to say that global soil protection strongly is neglected. We really would need something on the UN level to go forward with this. Next topic, water shortage and water pollution trends. Let's have the facts, some facts. Increase of freshwater use over the last century is 8-fold, and it continues to grow about 10% each decade. So up to 50% of water, as we heard already, is used or controlled by humankind. We do have falling groundwater tables. We have river waters which are often not reaching anymore the sea because we used them before. And we do have severe pollution problems like salinization, nutrient and sediment contamination, chemicals including plastics, pharmaceuticals, pesticides, biological depletion. Guardrails and institutions, what do we have? The suggested planetary boundary by Rockström is that the removal of 4,000 cubic kilometers per year of blue water would be the boundary. So this blue water is from rivers, lakes and groundwater. Currently we use 2,600 cubic kilometers per year, and this is rapidly increasing. Protection and sustainable use would be best achieved, we believe, by local to regional institutional controls and policies, because it is really a regional problem. However, the general water scarcity and the pollution does need global regulation, and there is something like the World Water Council, which is a NGO institution. It presently runs as a dialogue process, so there should be some improvement as well on this line. So let's have a look on raw materials, nutrients and pollutants. Extraction and transport of resources and the respective products really has increased enormously. As you see on the graph on the left-hand side, you see here construction minerals, ores and industrial minerals, fossil energy carriers and biomass is just increasing enormously across the last decades, especially since the post-war area. And this is closely connected with a huge increase in transportation. If on the right-hand image, you just see the blue line. This shows you the increase of shipping traffic. This is gigantic. It doesn't even fit in this graph. So we have in 1990 already up to 5,800 items, let's call it, in relation to all the other graphs here, which is enormous. And air traffic, for instance, under this respect at least, is of no importance. So what we do actually is we take out things, we make products out of it, we transport them, and we don't bother much what happens after this. So the WBGU vision is, of course, that we would have a full industrial metabolism concept. Whatever we take out from the earth, be it energy, be it materials, it should be followed. It should be followed during extractions, what energy is needed, what emissions are set free. It should be followed during production, during consumption, and of course during waste, so that we have a fully integrated image of our economy here. And of course the future will be especially in reusing whatever we have taken out as raw materials, as resources from the earth. So this, in the view of the WBGU, will be the new vision of an economy largely based on recycling. Some more figures to this. I will not go into details with corals, ores, crude oil, natural gas. We have the known problems. Let's just have a look at some examples in other strategic mineral resources like lithium or rare earths and rare metals, semi-metals. So lithium has an enormous growth rate owing to lithium battery use. It's up to 20% per year. However, there are quite some reserves. At the very moment, we don't have a problem with this, but again, the future will be here in recycling lithium batteries rather than getting out available other lithium. As to rare earth, rare metals and semi-metals, the image is different. Gallium, indium, neodymium, germanium, scandium, tantalum, platinum. All this is used either for photovoltaic industry, for catalytic converters, for optoelectronics, for fuel cells, for wind power, for mobile phones, and so forth. The demand will relatively rapidly outstrip production and reserves. So again, the solution would be to recycle these materials and to reuse them. Let's have a look at nutrients. Reactive nitrogen has become a huge problem because it's so relatively easy to produce. The production of reactive nitrogen is tenfold since the beginning of the industrialization. At the moment, it's about 156 megatons of reactive nitrogen per year, and this, of course, exceeds already natural flows in a great way. We expect 257 megatons per year for 2050. And the problem is that we can easily take the nitrogen just from the air using the energy-intensive Haber-Bosch process. So the planetary boundary suggestion would be to use only 35 megatons of reactive nitrogen per year. Worse it is with phosphorus. Phosphorus is very important as fertilizer, and we use now 3 times more in relative to 1960. Today we extract about 20 megatons of phosphorus per year, and the problem is that 50% of this ends up in the oceans, and that we only have reserves. We can't take it out from the air like nitrogen. So 60% of all reserves are in Morocco and China, and then South Africa and USA are also important for this. So we will run out of phosphorus soon. We either have reached peak phosphorus already in 2007, or according to other studies, this will be in the year 2030. And the problem is that this is not yet high on the political agenda. So the suggested planetary boundary would be something like 11 megatons per year of extractions. And then, of course, the solution would be also to recycle phosphorus. This is technically possible, but we are far from doing this on an industrial basis. There is more. Let's have a last look on the pollutants. So there are persistent organic pollutants, there are heavy metals. The general problem is that they are greatly toxic, strongly mobile, very long-lived, and their number and volume increases significantly. They spread globally and they accumulate in food chains. We still have a problem with lead. We have a major problem with mercury because it is still not so highly on the agenda, it's still not adequately regulated, whereas the lead problem is slowly diminishing, especially owing to the introduction of lead-free petrol. To sum this up, maybe we use this image of this figure of the planetary boundary concept again. We have tackled now in various sectors our problems, our trends in the Earth system. The major problem, however, is that this all interacts, and these arrows here should just give you an idea how everything is under interaction. Some examples we mentioned. So climate change acts on biodiversity. Of course, it causes ocean acidification, but on the other hand, biodiversity loss also can change the climate, loss of ecosystems like forests and so forth. So the problem is a very complicated one and a very systemic one. And we show you, and you should study this in more detail, maybe alone. We show you this table here, where on a matrix base you can see some interactions, some examples of interactions. For instance, climate change together with biodiversity loss can cause overtaxation of ecosystems and species' ability to adapt. Coral bleaching would be one example, or if you see the orange framed example here, biodiversity loss coming together with soil degradation can lead to increased erosion through loss of plant cover, and only very rarely we have positive effects, positive feedbacks, like that example here in blue. When soil degradation, for instance, comes together with climate change, there are negative effects because we lose carbon dioxide sinks, but we may increase the albedo, that means the reflection of energy again into the atmosphere. These are just a few examples here, and I'm summing up here. I hope I could show you that we have very dangerous trends in the Earth system, each of which we have to tackle, but the major problem is that everything is interconnected, so we need an integrated approach to try and solve these problems, and the Anthropocene concept might give us the appropriate view on that full context, on that systemic context. Let us follow this idea in the next episode. Thank you.